I am happy to see so many people here on a topic called error analysis. And I'll put a question mark here because the first thing we'll ask is what is error analysis? And it is related to something called statistics. And I'll put a question mark. Now, I'm always, I give this funny title called error analysis or statistics. And then I worry that how many people are going to be able to come in. And I have no idea why I am logged in as Nishant Singh, but I am Ranjeev Misra. So let's not have any doubts on that. Uh, Let me start with it. I mean, when I was in school, I may have a confession to make. When I was in school and till class 11, 12, the two most boring topics which I used to find uh, were biology and the second was statistics. In fact, I remember studying biology quite a bit, but in fact, I have complete mental washout on statistics. I believe I must have studied it in school, something about mean, mode, and all. We had to calculate things, but I have a complete blackout on that. And I have no memory of ever studying statistics at all when I was in college or doing my bachelor's degrees, and definitely not in master's degree also. There were some things which we did. Another thing which I found very mysterious and strange was something called error analysis, which we were supposed to know, and we were supposed to know in school time. And we were supposed to do error analysis in our laboratory work in physics labs, well, specifically in physics labs. I didn't understand why it was never done in chemistry labs. My knowledge was so poor on what is happening on this. And I didn't bother too much because it was okay. I mean, you passed the courses anyway without these two things. And they seemed very boring to me at all. It's much later I found out that there is a strong correlation between what I found boring and what was important. Uh, and why did I find it boring? The reason why I think I found uh, biology boring was even when I was in school and even now, our knowledge about biology is very poor. We didn't know anything about biology, while we knew a lot about physics, relatively. And that was the reason why I found it very boring because there was not much information on it. There was classifications. Statistics I found boring because of another reason. I didn't understand what. I mean, it seemed trivial. What is the reason for studying this kind of a funny subject? And error analysis, I knew no clue why we do it anyway in the whole thing. So much later, while I was doing my PhD or even post my PhD, started working on actual data and all, that I started realizing that in statistics in particular is a subject which is above the sciences. That is, if you don't understand statistics, you don't really understand what science is all about. And I had also started making mistakes about, and I realized how many mistakes I had done earlier about saying that I'm making a scientific statement when I was just giving an opinion. I'm going to, that any kind of scientific statement we make is based on statistics. And the the more amazing thing I found was statistics therefore is above science, and it is surprisingly to all of you will come is that it should be actually a subject of philosophy because it roots out into the main cause of studies. It answers some of the main questions which you are still confusing. Is what do you mean by knowledge? What do you mean that you understand something? What do you mean that this we consider as a law of physics? In other words, if you want to understand a law of physics like GMM, gravitational force is gm by r square, what does it mean? Understand the equation. But why is it a law of physics? Why is GMM by R 2.2 not a law of physics? You will say, obviously, oh, we have done experimental verification on that. What does that mean? What are the right questions to ask? And we'll find that this kind of questioning and answering goes down to the very basics of our understanding of human understanding of how do we get knowledge and what do we do. So in this 1 hour later, I'm not going to tell you about how to do analysis. I'm not going to tell you what is statistics or how do we do statistics. The whole idea here is to tell you that we need to, why do we have to study this thing? And go back to some basic levels, understand what is it that, why people are very excited about it. And I will not touch on and certain things which I would like to encourage is that, as I said, statistics is a matter of philosophy also, which is surprising to most people. And when you do philosophy, you'll have to give your groundwork of what you're doing. So the approach which I will give is a philosophical approach called the frequentist approach, which is the most common one. But there are other philosophical approaches. A more popular one, or prominent popular one among them is called a Bayesian approach. These are not scientific theories. These are philosophical statements on how do you get knowledge and what does it mean to get a number, or what does it mean to get a law in physics or in any sciences for that matter. So we will bring this thing down to the very, very basic level, that what you should have learned in class 8 and you did not, for a very good reason, that it was very complicated and probably it was difficult to understand when you were in class 8. But you did it in class 8, class 9, 10, something. You did it. And that is an experiment you did. And that experiment, everybody I think has done. And we will go back and look at what we had done. So we don't do the experiment here because we all know what it is. What you have done in one of the experiments in school is you have taken a pendulum, measured different lengths of it. You had pendulums with different lengths. And then you had stopwatch and you measured a time period t. And the idea of the experiment was to prove, was to that t is proportional to square root of g by L, I think, if I'm not mistaken. 2 5 factors on that. And first thing to do was to measure the t. You put square root of, or you, I think, is this correct? Yes. No, it's opposite, of course. Right, we increase that. Right? So what you do is you plot square root of L here in something called a graph paper, and you plot it. You make these points here, and then the instruction said, after you have made a point, you draw a straight line going through these points. Then you measure the slope of this point, slope of the straight line, and from there you can get to know what is the value of g, which incidentally was told to you was 9.8 meters per second wherever you are. So the way I told you was exactly the way I understood the whole experiment was. But it left out a lot of things. And let's, in this class, go back a little bit on trying to understand what. Incidentally, since I'm on the Blackboard we're working on, if you have any questions, just unmute yourself and ask. And that would be fine, because I won't be able to read a chat. So just unmute yourself and ask a question if you have it on the way. Okay. I think everybody remembers this. Horrible thing to do. You had a graph paper, you mark those points out, draw a line, find G, and then somewhere magically you were told you're also supposed to do some error propagation or error analysis, which will tell you how good your measurement of G is. So you write down, you get some value of G, and sometimes you write down plus or minus something. And there was a formula for doing that in some way. So that is the base. Let us now look back at this thing completely and see what we are doing. First of all, we are not doing one thing in this experiment. It's very important to realize that we are doing two things. And let's consider the first one. First one we are doing is, in scientific theory, what you do is you have something called a hypothesis. And hypothesis is an idea that if you have a pendulum with different lengths, the time period changes. So just general common sense, or looking at it, not common sense, looking at it from an observation, just looking at things, you cannot figure that if a pendulum has a longer length, it has a longer time period. Now, what you're trying to prove here as a law is, what is its dependence exactly? Does it go as root L? Does it go as half? Is it proportional? That is the root of the question. So if you want to answer that question, you just remove this thing and you're asking the question. First question you're asking is T proportional to square root of F? So we're going to spend a long time asking this question and asking, what does this question really mean? What does it mean that T is proportional to root F? So one meaning is that which we're doing, I will measure T and well, I'll have a ruler which will measure the length of the pendulum. Then I have some kind of a stopwatch and I watch it and I get some value and I mark it. And I say, it looks like as if T proportional to L is kind of a straight line. Does that prove or does that show that T is proportional to L? I mean, clearly, if we had points all along this instead of that, there were no dispersion, you would have said, oh, that's right, T is proportional. But let's take that statement again. What do you mean there was no dispersion? How small should the points be lying on this line for you to make a statement that T is proportional to L? When Galileo and others started working on this, they realized that this is an ill-founded question. What you can, because you're not measuring things accurately. So in those days, there was this concept, which we also learned, something called a least count. A least count was something which tells you that my ruler or scale, which I'm using to measure L, can only measure L to a certain least count, not accuracy, certain least count. That means it has marking on it only up to a millimeter. So since it's marked only to a millimeter, I will not be able to tell anything between millimeters. Least count for is 1 millimeter, and for your stopwatch, maybe it's like 1 millisecond. Now this gets me a little bit better into the framing this question much better in effect. I can ask the question that there is a box here And these boxes size and the height are the least counts of my two measuring instruments. Then I would say that if my straight line, passes through all these boxes, let me push it here so that it does pass through it. Will these come? Then I would say, oh, T is proportional to L, so T is proportional to root L, with a caveat, with a warning that this is done for a least count of 1 meter and 1. And what do I do? I say I should pass through the point. Now, but passing through a box like this is either it passes through or doesn't pass through. There's nothing like being in the edge because these numbers are defined as integer numbers of the least count. So the exact points and so this line will pass through, or if it is just a little bit away also, we can start complaining that it's not passed through. Some people will start worrying about this. This is, come on now. If this guy had just missed this out here, I would say that's not passed through. Then I would say the thing is wrong. If it just went through, I would say okay, it's all right. But that is becoming very nitpicking, right? You have some idea that this is fine. This is some kind of an idea that you pass through a line, now it works. In reality, this never happens. I mean, you've done the experiment. The least count of your things were 1 meter, 1 millisecond. You'll never pass it through a line. Your data point will still have a scatter. So there'll be points here. And there'll be points here. More importantly, before that, there was one more important thing which happened in science is all experiments must be reproducible. So it is in good practice, you find T as a function of L, I mean for 5 different values of L. Then you wait a while, go have a cup of tea, come back and do the whole experiment again with the same thing, just to make sure that they are all coming back and forth. This process of reproducibility has two reasons. One is it gets you a physical law that T is proportional to root L does not depend on time. I mean, it's always. That is how you can make it law. There's a all more basic reason why you do that is that you remove human error. Or you may have shaken up the table a little bit. You fell asleep when you're doing the measuring the length. You measure the length. You thought that the length was this, but you are, and then you confuse the tables up when you're writing it down. So it's always good to start with fresh again and write it down, and then you find. But often you find that even up and doing that, there will be differences. Why is that? First of all, you'll find that if you do it a couple of times, you may find that it varies. But after some time, if you do it carefully, you will find that all these positions will be in the exact position. They will not change after for repeatability. We never do that in our lab, right? So we have a lot of deficiencies when you do the lab. But suppose you do it like this, you will get values which are like this. Then you will say that why are there deviations? And the deviations could be of various different kinds. Could be that when your L goes larger, then you seem to deviate from here. But I could also fit it like this and say that when my L is small, I start deviating. So this is some kind of ambiguity which we don't know, but there is some kind of deviation here. What do you do? In that case, you have one answer that T is not proportional to root L. Before you jump to that conclusion of removing a hypothesis that there is T is proportional to root L, you start wondering that, more correctly, there's a gut feeling which comes in. Look, I'm not a very good careful on these things. There could be some mistakes. Yeah. Of course, I could have made mistakes. I repeat it. I be careful. I don't make mistakes. But then there could be other things going on. The other thing which is going wrong is systematics. Systematics is your ruler could be wrong. You actually had a ruler which did not have equal spacing ever. In fact, then you start wondering, how did a ruler ever get equal spacing in any case? It may be that when you go to higher lengths, the ruler is not exactly correct. This whole process is called calibration. So you now have to do another experiment, completely independent, to find out whether your ruler which you're using has equal spacings or not, and whether each of the spacings actually correspond to a 1 millimeter or not. The two things can happen. One is that the spacings are incorrect. The other is the spacings are all equal, but the distance between them is not 1 millimeter but 0.99 millimeter. But how did we define 1 millimeter anyway? The whole thing. So you have standard calibration tools. Like you'll have a ruler somewhere, which is actually there, which will have exactly 1 meter length. And you do exactly 100 divisions of it, you get a 1 centimeter. And that is considered exact for some. You take a reference frame. And then whatever your instrument is, you calibrate according to that to get the. But you can never do this second experiment, this calibration, in a perfect manner. So whatever is left out in your calibration, and sometimes you can never calibrate because you don't know whether your watch is working properly or not. You get systematic. There's another kind of systematic error you can get in, and you can try to that is, and you can first this kind of systematic error you keep improving by improving your calibration. There's another kind of systematic error which you come in is because your ruler may change in size depending on the temperature of the room in which you're working. So when you change temperature of the room, this experiment will change suddenly. So that could lead to also certain systematic errors. So how do you counter that? You counter that by this thing that you try to keep every parameter which you have control on the same during the experiment. If you do that, then those parameters which you could not keep the same, you will put them as systematic. A big question comes in is, how do I know that this deviation is due to systematics or it is really true that P is not proportional to 10? That is probably one of the most important and profound questions in science. How do I know? I repeated it. How do I know that I've discovered a new law, a deviation from a new law, or it is because of a systematic solution? And to do that, during the second calibration, you have to work out hard to find what is the magnitude of the systematic probability. And if you do that, then you go above the least count and make a bigger box. Now, the bigger box is above your least count box and it covers the systematics of the experiment. Now, once you see that, you pass through a line, you say, only if this line is deviating from the bigger box, and I have got good faith that I know how to do the big box correctly, then I will be able to say, I'm going to say whether T is proportional to root L or not. And how do I say that? I will still insist that all of them will pass through this point. And the other thing is systematic errors. Once I have controlled them, like for example, if I'm keeping a temperature and a reading constant, uh, if I repeat the experiment, I will get the same values. So I can do this. So in some sense, the philosophy here is I measure it, I take a block, I make sure that it passes through the line, and if it passes through the line, if it passes through these boxes, I will call it a physics law. And not right. So let me go ahead with some. If this was the case, it was for a while, life would have been real simple, and we wouldn't get into very deep level philosophy. The deep level philosophy started little after this. Understand? Given this introduction, now I'm going to do a. We are doing a much more sophisticated experiment than you did in your school. We have looked at these points. We got the best possible calibration we can go. What is the best possible calibration? We have a good idea on this calibration level, and we have a good idea on the least count. We have a good control temperature, but we also, and then we keep repeating the experiment. Now, what we want to do is we want to make the experiment better and better. So you bring down the least count and you decrease your systematics. You start going to a better calibrated ruler. You start improving your stopwatch. You start using. Don't use your hand to stop and start and stop. You have laser signals which pass through and exactly measure the time periods. And the length is measured not through your looking at visuals eyes, the digitally controlled measure which will not allow any systematics to happen. You start making this experiment finer and finer and finer. And your idea is these boxes will keep going down smaller and smaller, and we keep verifying whether how good this looks. And up till now, it's very straightforward. And I'll keep doing this, and as soon as it deviates from this box, I will say that my law is different and I have discovered something new. That was the plan. The plan went horribly wrong. The plan went horribly wrong for two factors. One is, I told you the ruler can vary with if the temperature changes. The way I do it, I keep the temperature identical. But how do I know what? It doesn't depend on the pressure of the air. How do I know it doesn't depend on certain other factors in the system? And so I say, okay, that is controlled in the system. The other problem which happens is these factors may change in time. So, for example, if you know the temperature exactly, but there's a fluctuation in the temperature there. So when you make the measurements, it's not exactly always the same point, but will be within that box of your bigger box of systematics. So you're okay with it, right? So then you pass it. Pass it. And as I improve my systematic, as I make better and better control things, I'll go. The other point was that in this kind of experiment, like I said only temperature, pressure, and all. But many times when you're measuring, let's take your stopwatch. The stopwatch can be sensitive to a whole host of things. It can be sensitive to temperature, it can be sensitive to pressure, it could be sensitive to electric signals going around, it could be sensitive to the fact that whether you have put a fan on or not fan on. There could be large number of these kind of factors which can cause minor variation. So every time you do an experiment, you will find that there is a slight in the hood. So you can never get below that value. But this was not considered very serious. Because they said that at one time, I mean, it's just a human limitation of the laboratory. If we make better instruments, we will make smaller and smaller systematic instruments. But that time, we did not know about quantum mechanics. What we found, look at quantum mechanics is an important thing which comes in at at many level in precise instruments and all, astronomy definitely, is that things are quantized. It's not a quantum mechanism, but things are quantized. For example, one of the main things is quantized is photons. And if I'm using a device to measure the number of photons coming in, or now we know electrons are quantized, there are number of electrons. It's not quantized. It's not that there is a continuum of charge. So when I take a measuring device, I'm actually measuring numbers. 1, 2. This gives a fluctuation. So if I have a source, I cannot have a source which is giving me 5.3 photons per second. Suppose it's on average is giving 5.3 photons per second. I will never measure 5.3 photons per second. I'll either measure 6, 5, 4, 3, an integer number. This gives an intrinsic variation to the source. So either make it big, louder, larger, but this variation will always be there, and there will be a scatter. Let me verify better. So now what we have done is we have these experiments which are very, very fine. The scale has gone up. I'm still drawing my line through it. But now I have a problem that every time I come and do this experiment, this point will change. And I know it should change. So now I'm going to ask again this question. What does it mean when I say P is proportional to root L? First, let us ask that question. What does it mean? Experimentally, the answer to the question is no. P is not proportional to L. You measure something today, it comes here, something will come there. So it is not. The way out of it, you say, is that wait. P is proportional to L in the sense that if I do this experiment many times, I average these values which I get, then I'll get different values, and I get a average value, which I'll mark with a big cross. And this average value will go through the point. This is a tricky situation. If you understand, this is where I say philosophy comes in. But I was doing an experiment where I did this 5 times, and I got this value. But if I go and do the same experiment 5 times again, I will not get the same average. I'll get a different average, but it'll be closer by maybe. So this is a philosophical statement that T will be proportional to root L, given that we do this an infinite times. Because when you are doing this experiment multiple times, you get a different results out here. And so the question which we're asking is what do you really mean by T is proportional to root L? When every time we do an experiment, we'll get a scatter where it will not be a straight line. You can say that the definition that you can say is that if you do this experiment an infinite number of times, then this equation holds. Fine. So how do I know if it deviates from that? You have to do it an infinite number of times to get this thing to work. So unless I do it for infinite time and I find that it does not go through, then only I can disprove the statement. And in physics, everything is about disproving things. So we have a major philosophical problem. How do you disprove a statement which says that you have to do this experiment an infinite number of times to disprove it? This was a very important problem. And the solution which I'm going to give you right now is called a frequentist approach. And I would like to, this is the most popular approach. Nobody mentions it as the, but This is the most standard way. There are many other ways, like a beautiful way called Bayesian approach, which has a different. The mathematics is very similar, but the philosophy is different. They don't take this approach to solve this problem. What is the problem? The problem is how do you prove that this is not true? Because unless I do this experiment an infinite number of times, I cannot prove it together. So what you ask the question is, given a value of root n, and given a point which I've got here, let me say this is my measured point. Given TO, which is my observed TO, and the measurement which I did in L, this L I'll keep fixed L. What is the probability that the actual function, the actual value of the time period, average of T would be TA? Okay, let me rephrase this question first. Let us assume that this is correct. Or let's assume that, no, that's correct. Let's assume that when I do at a given length, I measure a time period infinite number of times, I'm going to get a value which I will call TL, TT, T true, which is the average T. I could write this also in a better way and say that this is the average T provided I've done it infinite number. There is a value like that T. For any time I give it, or any subset of time, I mean, even if I average of 5, 10, 15, I will get a value of T observed, the time period observed, which will be different than T alpha, T infinity. Okay. So you can ask the question, what is the probability that we will get T0 given that the actual average value was T? I don't know how to find that out. I have no idea what but I find this probability concept. And then I say that, so I can, if I can measure this, or if I can estimate this, sorry, not measure, if I can estimate this, then I can find for any given straight line like this, which is my T proportional to L, and I get observation like this. I get measurements like in these points. I can find what is the probability that I would have got a point like this, which is away from here. What is the probability I would have got a point like this, away from here, away from here, away from here. So I can then ask the question, what is the probability that I would have got this set of 5 or 10 points? What would be the probability? I would be saying that the probability is just a multiplication of these probabilities. P1, P2, P3. Let me repeat. I have an observed measured T as TO here. The true T is this value. I'm asking the question, what is the probability that I've got a measured value like this if the T was like this? That is P1 for this. When I do it for all of them, and I multiply the probability together, and which tells me what is the probability that if this is the real true line, I do a measurement, I will get these points. The question is very important here. So I will repeat the question. I repeat the question. What is the probability that given that there is a straight line like this, then I would get these measurements for a given instant? If you repeat the experiment, you will get a very different answer, always. So, but what I would like to say is that if this probability is high, that is large, then I guess it's okay to say that that the data is consistent with T is proportional to. What does this large mean? And what does it mean? And what should be the probability? The probability that I'll get these points again, or in any these specific points in any experiment is 0. Did you understand why it's 0? You see, if I repeat the experiment, I will never be able to get the points again to be exactly in the same place. So the probability of something happening, this thing happening again is 0, and that's the probability we're talking about. In that case, all this probability will multiply, this probability will be 0. So that is not a good question to ask. What is not a good question to ask? What is the probability that I will get these measured points given that there is a trend? Then you ask the question. This is the confusing part. This is the part where we say that then how do we proceed further? Then you ask the question, what is the probability that if I repeat the experiments many times, let me call this PO. This is the probability of the experiment that for the particular experiment I got. And this in general will be a very small number, or actually nearly 0. In fact, it's mathematically 0. That I would have got exactly the same value. Let me call that PO anyway. Again, speaking, our logic says that a PO should be large for us to accept this idea that the T is proportional to root L. So I asked, what is, and when I measured this probability, I got to be 0. So now I'm in trouble. So I rephrase the question. I will rephrase the question as, what is the probability that if I do this experiment a large number of times, infinite number of times, I would get a probability P O prime, which is smaller than P O. This is confusing, so let me repeat this whole thing. I've asked 2 questions. My first question is, I have done an experiment and I've got these values. TO, P5. I did actually get these values. Then I asked the question that if T is proportional to root L like this in a single line, I asked the question, what is the probability that I would have got these observational points, which should be P1, 2, 3, 4, 5 multiplied together. This by itself tells me nothing. So I ask another question, completely independent question that. What is the probability that if I did this experiment an infinite number of times, I would have got, or how many times I would have got this measured probability, PO prime, to be less than the one which I have got right now. This is really confusing. And I want to emphasize on you that this is really difficult. But I would, before I stop, I will just tell you something which you may have known, so you can make a connection. Suppose I say that the probability that you get a T given T0 is T1 is exponential minus T minus T0 whole square. That is, the probability is distributed as a Gaussian function. How do we get this? I will come back to it little bit soon. But let us say, suppose I know that this is the probability. That if I have the actual value of actual value of t is, if I did experiment infinite time, is this. The probability that I get an observed TO is given by this value, and this is some sigma which I can estimate. So if I take this whole P0, this will be multiplication of all these things. So it becomes, and multiplication means that this will add up like this. For the first one, for all of them. And then I take a log of this value, and that will become something like this. Minus log of this. Just to give a nomenclature so that you know the namings of these things, this, the minus log of P0 is called a likelihood. And if this is in like a Gaussian distribution, then this is called the chi-square. Why is it called chi-square is another thing I can go to. Whenever you calculate the chi-square, so for all these 5 experiment points, I can calculate chi-square and I get a value. But actually, I should put it in this form and find P0. I'll find it to be very, very small. But the question we ask is this one. That what is the probability that when I got a chi-square larger than some value of chi-square minimum, which I decide, what is the probability of that happening? Wow, that, or put it this way, that if I did this experiment 1,000 times, what fraction of the time I would have got chi-square lower than this value? Chi-square. I mean, chi-square greater than the value of chi-square. So, just to make it representative, suppose this is all mental experiment. I do this experiment thousands of times. I would have got a distribution of chi-square. These are number of ones. And the question you're asking is, the chi-square value you have got for this particular experiment, where does it lie? And then again, you make a jump of fate and say that I will decide that when 10% of the cases is like this, I will accept it. If not, someone else may say, why 10%? Why not 1%? That's perfectly valid. You have to define your confidence level before, and based on that, you are going to say this kind of thing. It's going to become extremely messy. The actual way how you do it is complicated. But what I want to point you out is why we have to go through this very carefully and study. That is because when you say a statement, the t is not proportional to root L. See, when you say t is proportional to root L, that's known science. When you say t is not proportional to root L, you are going into the real advancement of science. In the hope that something has deviated. You will have to go through this kind of argument, get chi-square values and process and get the value out. But remember, even when you do that, you are using a particular philosophical approach where the number of experiments you will do is infinite. You imagine it, and under infinite experiments, again, the question you asked is, what's the probability I would have got this kind of a bad result in? So when you see a deviation from root L, suppose in your actual experiment you find that only, let's say, 1 in 100 of my such experiments would have seen it deviate like this. Is it worthwhile? What people do is they do more experiments to make this number better and better to find out. I will stop here with some quick statements. I have not done, up till now we have just done one part of your high school experiment. Only the first part. That is, take this line and find out whether this line is matching. The second part of the experiment was to find the value of g. That is, you take the slope of this value, so, and you find what is this value. G was, so t was proportional to root L by g. So the slope of this line is square root of 1g. So the idea was to find the slope, and from this slope you find what's the gap. We haven't even come to that. That is called parameter estimation. That has its own set of philosophies. Is there something like a real G? And what do you mean by a G when you're doing this? Again, it says that if I do it a million times, I will get some number which is equal. But I am comparing with one slope here. So I could actually calculate this chi-square for different values of this parameter S, the slope. Then this question becomes more and more murky. Is how are you saying that? So you have to ask a complete question that if G was a certain value, what is the probability that I would have got a chi-square as bad as this one, as large as this one? So the question becomes very convoluted as we go on for parameter space. And when you have larger number of parameter space, systematic errors, this becomes complicated. Complicated means you have to understand what you're doing before you can make an interpretation correctly. So, and all depends on whether you take 10%, 20%, 90% confidence levels, it all changes. And last thing is, how do we know this magical thing? How do we know that the probability is distributed like this? One is you can do an experiment. I can go ahead and experiment and do it 100 times and I see, this looks like a distribution. But that's a faulty one, right? Because if I've done an experiment like that, I'm going to take the average and I want to know whether the average is distributed in the probability like this. So, many times we do not know this probability distribution. And this causes a lot of trouble. However, there is a particular theorem which I just write down. I won't go through it because of lack of time. Something called the central limit. I just want you to here know about this. You can read about it later. The central limit theorem, I'll leave it to you, is the reason why we can with some confidence say that the probability goes like this. And it is the central limit theorem which allows us to do a lot of the science which we're doing now. If the central limit theorem was not valid and we had no clue of its probabilities, science as we know it now would not have been possible. We would not have been able to do experiments in good. So in summation, I have not told you anything about how to do error analysis. I have not even taught you how to do statistics. My only intention in this course was just to give you a flavor that this is complex, interesting, and important since it is the basis of all our scientific knowledge. Once we understand this properly, we understand science in its generality. Right? So I will pause here, stop here, and any questions, I can take that.
Hello, sir.
Yes.
Thanks for the amazing talk.
Yes.
I had one question. So, in frequentist approach, we consider unknown parameters. Oftenly consider unknown parameters as constants, and that they do not contribute in the probability. So, does this affect the results?
No.
Or our hypothesis?
No. It is not that we consider. I mean, it's a wrong way of looking at it. What it means is that in frequentist approach, we are not biased by any other previous experiment. So suppose I want to find G in this experiment. I will not do what all of you must have done when you're school. That, you know what? Let's fix the number so that it comes close to 9.8. Right? Uh, but that incidentally is now legal. In the legality comes in is that you could have a bias. Somebody would have told you that this number is close to 10, and then you work around and whatever. That is taken into account in Bayesian analysis. In a frequentist approach, the difference is in a true frequentist approach, you're not supposed to cheat. You cannot say that I have a prior idea or some concepts that G should be around 10. Whatever you get from experiments, you get it. So when you do the philosophy and you check for numbers, you're going to check for all possible values of G in the probability distribution. You're not going to restrict it. Did I explain your answer question properly, Roger?
Yes, sir. Thank you. Thank you so much.
Yeah, can we just reduce the probability terms if each probability is related to the subsequent probabilities?
Each probability is related to the subsequent probability means these terms are related to each other. Huh? Oh, yeah. That will drive you crazy. It doesn't make it easier. It just kills it. This becomes a major problem. That is, it is a doubly simple problem. That suppose I'm measuring the length and I measure t, and if whether I do this first or measure the length twice the length first or this one first, it changes my result. I'll be in deep trouble. This expression becomes extremely complex. If I understood your question correctly, that is, if the probability depends on my previous experience. Did I answer that question, or did you have something else in mind? Yeah, I mean, it doesn't make it simpler. At least it makes it much more difficult. If your experiment depends on the order in which you've done experiments.
So these concepts of likelihood and then this threshold and all also appear in the Bayesian approach in hypothesis testing and everything.
Of course.
So how is it exactly like different? Like, is it just about the way we interpret it, or is it also?
Strictly speaking, there are mathematical differences, but in reality, the real difference is philosophy.
Okay, sir.
It really depends on what do you mean when you say, I think T is proportional to root of value. The frequentist people will say that as far experiments right now goes, we think T is proportional to root of value. The Bayesian people will say that I have a belief that T is proportional to L, and they'll give a number to that belief. So that is the two different approaches. So science, according to Bayesian, is not based on fundamental the present experiment you're doing. It's fundamentally biased in your previous experiments. That is the difference in the philosophy between, and it takes a long time to think through it, which one is probably correct. Incidentally, that is one of the, I think the Bayesian thing is important for all of you to realize that the Bayesian formulation is more like what actually we human beings think, not what we are supposed to think. So, for example, if you do an experiment which proves that Einstein's special relativity is wrong, what does that statement mean? What do you mean you have proved Einstein's special relativity is wrong? You have measured an experiment which light is moving faster than the speed of light. The kind of probability threshold and everything you have to do is to be very, very serious before anybody will believe your experiment. Right? Belief comes in. While if you say that I have found out that the conductivity of copper mixed with magnesium is certain value, nobody's going to doubt that experiment very vigorously. Right? This is where the Bayesian philosophy comes in, is that we had a prior knowledge that the speed of light cannot be exceeded from previous experiments. We are not going to just look at this particular experiment and take its face value. While in pure science, something which has been taught in pure science with some frequentist approaches, we will say, no, every experiment should be treated independently. And then if you want to join, of course, you can join them. You can take two experiments and find the probabilities together, but that's a different approach. Each experiment should be treated separately. Some philosophical level changes in that. There's also a mathematical advantage of being able to give prior belief that, for example, if you're the good example is if you're measuring, let's say, the mass of Jupiter as a parameter, I can completely, without problem, say that the mass should be positive. And this cannot be incorporated in frequentist approach. Frequentist says it could be negative also. Let's check that also. But in other approaches, you can put this constraint down that at least the mass will be constant. But on the other hand, if you put the constraint that the value of the G constraint is around 10 and you get 9.8 as an answer, you'll be wondering whether the experiment was actually required or not. You already knew the answer, right? So why did you do the experiment? So there are two extremes which can come in.